Okay, let's get going. So it's going to be a very practical week this week. We're going to be talking particularly about the programming model today. Um, yeah, so we're going to finish off the Rust as well this week, and then we can spend a lot of time writing programs. I think we got about this far in the lesson 4 notes last time, so I'll just finish off this, and then we can move on to the lesson 5 notes, and it'll be a good recap as well. So just to remind you, first of all, everything in Solana is an account, which is slightly confusing, but there it is. Programs are also accounts, but they're special types of accounts. They're accounts that are executable. And if you remember, we have this situation where it's different from, say, Ethereum in that the programs themselves don't have state. And so obviously we want our programs to be able to operate on data. We want them to be able to do things. We want to be able to persist data over time. So we do need accounts. And the difference is that the data that they're going to operate on, the data that is going to be persisted, is going to be held in separate accounts. And then the programs will be acting on those accounts, these, if you want to call them, storage accounts. Now, we're going to go through some terminology around ownership of accounts, etc. And one point to know is that when we create the accounts, they're created by the system program. And so you will see that. And then we can, ownership can be transferred. And so programs, for example, will get owned by what's called the BPF loader. But data storage accounts will typically be owned then by a program. Okay, so I've got some examples here. So we've got an account. This has an address, a public key. We can tell that it's not a program because the executable is set to false, and it has nothing in it. It's an empty program, but it has a particular owner. Sorry, that's the second one here. Sorry, this one here. So it's, yeah, set to false. The There's nothing in the data, it's just zeros. And then its owner is this address here. Okay. And then we've got that address itself is a program which is owned by the BPF loader. As you can see there, the owner is the BPF loader upgradable. And that is a program, and the data within the program is not data in the same way that it is in an account. It's bytecode. So that's what you see at the end here. Okay. Now you may remember from last time that I explained that when we interact with programs, where these programs start, there is a single entry point, and it's quite standardized the way that we interact with them. So we have this single entry point, and then there are 3 arguments, the 3 things that we're going to pass into that entry point. First of all, there is the program ID. So this is something that can be used to check that we are in fact interacting with the correct program. Then we can pass in a number of accounts, and this is so that the program can interact with data and can update data if it is going to. And then we can pass in instruction data. And if you remember, in Solana, we can have a set of instructions, and those set of instructions make up a transaction. And those instructions will be telling the program what functions we want to call, so for this particular transaction. Now, one other oddity about the way that we interact with our programs, the way that the programs run, is that the return value we get really just indicates whether the program runs successfully or it's an error code. We don't get a return that shows us what has been updated in the system. Okay, so when you send a transaction into the system, this can start a program. That program will run some code, And at the end of that, all that we get back is something to say that that ran successfully or that there was an error. Okay. So what that means is that if you want to know what that program did, what changes were made by that program, what change of state was made by that program, you will then need to check with the network and see what has changed. You would need to query an account, for example. So that is something else to bear in mind. And we'll talk more about that when we look at interacting with programs. But you need to know it at this time, because when you look at the entry point for a program, then you'll see what the return type is, just an OK or an error code. Okay. So yep, as I said, yeah, the program ID. This is the public key of the program. The accounts are there to provide data, allow us to update that data or to read that data. There are various aspects of those accounts that we will certainly look into in more detail. We need to know things such as whether those accounts are going to be read-only, whether they're going to be writable, and if we're going to be writing to those accounts, they will need to be signed for. Okay. Um, Now, the actual makeup, the kind of architecture, the design of the accounts that you pass to the program is going to depend very much on what the program is trying to do, and also what programs are going to be called. So you can see an example here. We start off, our clients will call a program, and then maybe that is going to interact with one account that is where it's going to be writing data, another account where it's reading data, another account could just be a wallet. So depending on the type of application you have written, the accounts that you pass obviously are going to vary in their function. Now, it's also possible that one program can call another program. So we've got the example here that our client calls program A, but then that program is also going to call program B or program C. In specifically, the instructions will be specifying what should happen there. Now, in this second case here, where we've got programs calling each other, we need to have special types of addresses, special types of accounts used. You may remember from last week, I mentioned this, that we want the ability for programs to be able to sign accounts, and that's particularly for this type of situation. So I mentioned instruction data. So this is passed to the program. It goes to the entry point along with the accounts, and that is going to tell the program what functions within the program we want to call, or any other extra information that needs to be passed to the program that is not part of the client, that is specific to this, sorry, not part of the account, maybe that is specific perhaps to this transaction. Now, one thing we're going to see as well is the concept of serialization and deserialization. So when we are passing data such as accounts or instructions, what is usually the case is that these will be serialized, and we will need to deserialize them to interact with them and then serialize them again. This process is there really for efficiency, so that it's a way of encoding the bytes, the data, or the accounts or the instructions. It's a way of doing that to make it more efficient for them being passed around. But obviously, it's an extra overhead that we need to do when we are writing our programs. We need to be aware that we have to do this. The one thing we will find later on is that Anchor, the framework that we'll be looking at next week, this will take care of all of that for us. But if you're writing with the native Rust, if you're not using any framework, then you need to be aware that you will have to do this process. Of course, the process itself is done via libraries. We'll be able to call libraries to do that. But we still need to be aware that that process has to happen. Now, a point about the design of our program, and certainly again we shall come back to this later when we think about security, is that we'll have a number of instructions that are going to be sent to the program, and the the person who is writing the program should be aware that those instructions could come in any order. When you're writing a program, you should not make assumptions about the order that instructions will appear in, because if you do that, then it's possible that somebody could change the order and achieve something malicious. So you need to design your programs so that they will work correctly, even if the order of the instructions changes. All right, good. So let's just recap that program flow then. So we pass the accounts, instructions, the signatures that are associated with these. We pass these to the entry point. The entry point will then pass on these arguments to other modules. So I'm saying here, I think called the processor module, and we'll have a look in a minute at what modules you tend to use. Now, the first thing that we will need to do is to get the instructions to work out what functions are going to be called within the program. And so we usually have an instruction module which will take the instructions that we've received and decode those. So work out how to use those and how they're going to interact with the program. And once we have that, then we will know what functions are going to be called in the program. Once we have that, we can do some computation, we can read some state, we can read, or we can think about reading from accounts and writing to accounts. But again, when we want to do that, we will have to have the accounts that have been passed into the entry point. And also we will need to think about the serialization. Now, if as this is happening, we get any type of error, then the program will revert at that point. And remember, the transactions are atomic, so if any instruction fails within the transaction, then the whole transaction will fail, which is useful. That is typically what we would want to happen. Okay. Now, that's what is happening really on the program side. Of course, if you take a step back and think what the client is doing, well, they first of all need to be aware of what the program looks like, what the interfaces are into the program. And so we have this thing called the interface description language, which is a description of the program so that we know how to call the various functions. We know how to create the instructions. So on the client side, the thing that's going to call our programs, we need to connect the network, get the instructions ready, assemble those into a transaction, submit those to a node, which is an RPC call. That will then start the program, will start the computation in the program. And then that will hopefully succeed and we'll get back an okay to say that it worked. But then we may need to read some modified account state because we know that the program worked okay, but we want to read and check maybe what changes have been made to the account. Okay, so that's what you do on the client side, and on the program side, then you've seen what that looks like in the entry point. And we'll look at what the client side is like, and we'll get some practice of that next week. But for this week, we're really going to concentrate more on the program side. In terms of the workflow, as developers, what we do is we will start off with some Rust code. So we're really concentrating on Rust in this particular bootcamp. So we will compile that to create a binary that will then get deployed. And once it's deployed, then we can interact with it. Of course, you will also want to be doing testing as well. within this, and we'll explain a little bit more about that later. Here are some details about the how we can compile, etc. Yeah, you're typically going to be using cargo to do this, so that will yeah, that will pretty much take care of everything. The cargo.toml file, this is the configuration file that you can use to set up details there. For example, we may have the program name, we may have details of the network, etc. Once you have your binary and you want to deploy it, then you can use the command line that we saw last week. So you can use Solana program deploy and then specify the path to the binary to do that. So the interaction, we've kind of explained that. This is just saying a little bit about what you can expect to see in accounts. As I said, there's going to be either a program if it's an executable account, or it's going to be some data that's going to be stored in the accounts. All right, and there's some links there to give you a bit more detail about the accounts. The cookbook is useful because that gives you some practical examples as well. All right, let's quickly look at some examples of traits in Solana as well. So this is a little bit of revision, just to remind you about traits. We saw these last week, how they were used in Rust. So remember that a trait is like an interface. It allows us to group together, say, data types that act in or going to behave in a particular way. It allows us to constrain behavior and specify how something should behave. We have this ref self that is used then to refer to the data type that we can then interact with. So within our trait, as we describe our trait, obviously we don't know what data types are going to implement that, but we can use ref self so that when they do implement it, they can refer to the data type. And here you can see we've got a trait with a number of different functions. And in this case, we are looking at, say, items that you may find in an account. So we could look at some details that will be held in an account. So you could have things to get the owner or an admin, etc. We could have getters and setters, and then things to summarize the details, like printing the details. Okay. So as it says, if you're going to have functions that are common and are going to be used in many structs or in many data structures, then it makes sense to define a trait to encapsulate all of that. If you remember, the way that we actually implement the traits is by the impl keyword, and then you can specify the actual functions. You can provide the function bodies that have been specified within the trait. So this gives an example of what we might want to have an account looking like. We might how the data area of an account may look. So we can specify a struct to say that within this account, within the data in this account, we're going to have these three items. An admin, so we've got a public key for that, a public key for an owner, and then a U64 to say an amount of something. And then having specified that, we could provide, we could use our trait details to then interact with this particular struct and return implement the various functions, provide the function bodies to get those details out. It could be the case that we need to also to serialize and deserialize as well. So you may see something like this with the pack and unpack to do serialization of data within the account. Yeah, and then you could call that unpack, as you can see here. And of course, as you see with the results here, we could get an error. So with this, we've got the question mark at the end, which allows us to handle the error. It will then throw that back up the stack. But if there's no error, then we'll get the item that we're expecting. Okay. Right, so that's the end of the lesson 4 notes. I'll move on to lesson 5 now. I just put this in. This was well, a couple of months ago, I think, but just to give you an idea of how Solana has done since inception. So lots of transactions, over 400 billion transactions, and the volume, yeah, almost $1 trillion in volume as well. So pretty impressive. Okay. So let's dig into the accounts in a little bit more detail. So the way that we're going to be using them, really, we're thinking about the accounts being used and owned by programs. But of course, a single program may may own many accounts, as we saw in the diagram a little earlier. Within the account themselves, there are a number of fields that we will be using. So we will be able to get the key, the address of the account. We will want to know whether it is being signed for, whether it is writable. We want to know the balance of the account. We want to know the owner, the flag to say it's whether it's executable, so if it's going to be a program, and then the rent epoch, because we need to pay rent on the storage that we have within the network. Now, the data area is where we then have data that is specific, for example, for this program. And that's where we would then be creating a struct to specify what that data is. Now, something that is quite confusing is this terminology, the owner versus the holder. And this is to do with the way that accounts are created and used. And the owner is not the person who owns the private key of the account. That is the holder, and it is the holder who is allowed to transfer balance from the account. But the owner is the person that can amend the data within the account. And the owner initially is the system program. So by default, when an account is created, it will be the system program that is the owner. If you then use that to store some balance, then you would be the holder. So you will be able to transfer that balance, but the system program would be the owner. Okay. So this is quite different to what we see on Ethereum, and any any account can store state, but the programs themselves, the ones that are marked as executable, all they are going to be storing is bytecode. Okay, I think I've pretty much said all this already. There are some special types of accounts. So there are some special programs such as system, stake, and vote, etc., that do various system functions. We're going to be more interested in the data accounts, the accounts that are owned by programs, the accounts that programs are going to be using. So the programs that we write are going to be using accounts. And of those, the first type here, the system-owned accounts, these are the common ones. And then we also have the program-derived address accounts, the PDA accounts, which are a little bit special. So why are they special? Well, as I explained, and I showed the diagram earlier, we often want programs to be able to call other programs. And in that case, those programs may be passing accounts to other programs and authorizing updates to happen to those accounts, in which case the programs need to be able to sign for those accounts. But obviously that's not something that we can do in the normal sense, because we would need a private key for that. And we can't store a private key in a program, because then that would be compromised. Everything is public. So we have to have a different mechanism to deal with that situation. And to do that, we have these things called program-derived addresses, where it's an account that really is tied to a specific program. And that program can sign for that account, but it can do that without using a private key. So it's a very special mechanism that can be used. We also have the requirement, if we do that these special accounts have to be created in such a way that there is no there's no private key that could sign for them, because otherwise then that will be a kind of a compromise as well, if somebody could sign for them as well as the program. So we want only that program to be able to sign for these accounts, but we want that to happen without a private key. Okay, so it's quite a special circumstance. And something to think about when we're dealing with these is that you can think of them as being found rather than created. That may be a better way to think of it. But yeah, we'll come on to the mechanism for that a little bit later. Okay, so yeah, this is just a summary of accounts there. Coming back to the fields, they'll have a public key. They have an owner field, and that could be they could be owned by a program. For example, the programs will be owned by the BPF loader, which has that address. As I said, if it's a PDA special type of account, they don't have any private key, and by default, the accounts start being owned by the system program. There are some rules around what can be done with the data in the account. So the data in an account can be changed by the program that owns that account. But any program can credit or credit an account, or can read data from an account. Now, we start off with the system program, so that is the program that does the initial ownership, and then that will set up the data within the account initially, and then it will be able to assign ownership of that account to, say, a program, but that will only be able to happen once. Now, what about programs themselves? How are they created? Well, typically we may well have these first two steps there already. So the developer will have a key that they're going to use. They'll have some funds associated with that. Then when they have their executable, they need to get that the bytes for that program. They have to be put into an account. So the system program will have to allocate space for those bytes. The system program will know that this is an executable, and so they will then assign that account to the BPF loader. We then want to actually send the bytes to the system to fill in the area within the program, fill in the byte code. That is done in a series of steps. It's not done all at once. That will happen in pieces, as it is said there. And then when that has all been completed, then it will be marked as executable, and then you will be able to call that as a program. Okay. So to dig into it in a little bit more detail, we have the concept of transactions, which consist of a number of instructions. We have the Solana runtime that is controlling everything. And that is able to take the instructions that come in a transaction and pass those to the program. And that is going to do some function. So, for example, it could be just transferring some balance from one account to another, or doing something much more complex. But as I say, whatever it's doing with these instructions, the transactions themselves are atomic. Okay. Now, one of the reasons that we're able to get very high throughput with Solana is the fact that we can do parallel processing of our contracts. And if you remember last week, we spoke about this a little. We spoke about some of the potential difficulties that you get when you're trying to do parallel processing. And in order to be able to do that, the SVM needs to know what accounts are going to be used by these instructions. So it needs to know what it can safely do in parallel. So it can then take in transactions and which are containing many instructions and sort those so that it can then do a fair amount of those in parallel, but do that safely. So the system itself, the SVM, needs to know before it starts executing the instructions, it needs to know which accounts are going to be used by those instructions. And we'll see later on that this sort of adds a kind of complexity to the way that we do certain types of transactions. Now, this this is not a trivial thing to do, to be able to work this out in advance and to sort out all of the transactions and run many of them in parallel. And we can see that other blockchains are starting to do this. Some are doing it directly, like also doing things in parallel. Ethereum hasn't quite got there yet, but they do have a special transaction type that tells the virtual machine what state is going to be updated. And so that can kind of help with caching and things like that. So I think overall we are moving in that direction. The fact that we're getting advanced information, we're getting information ahead of time about what state is going to be updated, and therefore we'll be able to process the transactions more efficiently because of that. But part of that processing is going to involve checking signatures. And when we have accounts that are going to be updated, they will need to be signed for. We need to be able to check the signatures that are coming in these transactions as well. But also, if we can process things in parallel, then that means we can also check those signatures in parallel as well. And so that is something that certain types of hardware will be able to do better. So, for example, GPUs are better able to process in parallel. Again, this is all helping the throughput of the system. What do the transactions themselves look like? Well, we will have a number of instructions and accounts that are going to be involved, are going to be used by this transaction. We will need signatures as well. There is some metadata to do with the accounts that are being signed, which are being updatable, etc. And yeah, that the instructions that are involved there as well. We also need to know the program ID. We need to know which program we're going to be calling. And then there may be some arguments that we're passing to the program as part of this particular transaction. So there's a lot of flexibility in the way that we are interacting with our programs. So we've got the instructions that are specifying what programs to call and what functions to call. And then also we have this buffer, the call data, which is there to allow us to add in specific pieces of data when we're calling the program as this particular transaction. Now, when you're writing your programs, it's useful if you can see what is happening. It's useful to have some kind of a debug log, a way of printing out what's going on. And so for that, we have a macro, the MSG exclamation mark macro, which will output text to a console for you in Solana. So you'll probably want to make use of that as you're writing your program, certainly initially. Now, when you start writing your programs, you may just put everything into one file. If it's a small program, that could well make sense. But over time, you will, as the program grows and as you want to use best practices and make sure that it's going to be scalable and modular, you will want to break your program into modules. And there is a convention around this that you will see. So these are the modules that we tend to write when we're writing our programs. The first one is the way of registering the modules, that are going to be used. So that's really kind of like an index for all of the rest of the modules. And then we'll have one module that is the entry point to the program. One that is there to handle the instructions, particularly deserializing the instruction data. The main logic of your program is going to be in processor module. But then we also need a module that's going to handle the state within our of the state that we're going to use. So reading from accounts, writing to accounts, and doing the serialization and deserialization, etc. And then we will probably have a module that is going to be able to handle errors and specify what errors there are within our program. So that's a common breakdown of the modules that you may use. You may see this when you look through source code, that it's broken down in this way. So what tools can we use for this? Well, there is the Solana Playground, which is a good start. I'm going to show you that in a second, and we can have a look at some an example program. We've seen already the command line, and there's details of how to install that in the lessons from last week. And then you can create a local validator. You can create your own local little cluster that you can then test against. So you can deploy your programs to that and use that for testing, and you're not interacting with anyone else. So it's quite useful. And as I said, next week we will look at the anchor framework, which takes away some of the or handles some of the sort of mundane tasks that we need to do. But before we use that, I want you to understand what those things are and understand what's actually going on in the programs. Okay, so let's have a look at the playground. Okay, so this I've got something there already. Let me start from scratch. So we can create a project by clicking on the plus up the top there. We get a choice of the type of project we want to create. So next week we'll look at Anchor. You can write in Python, but we're not going to cover that in this course. So what we're going to choose is the native Rust. Let me. Oh, I already got that. Okay. Okay, so here it's created a program for me. Just to show you what we have on the left-hand side, this is the name of my project. I can delete it, I can save it to GitHub, etc. And then these are some files that it has created for me. So this is the file we're going to look at next. This is our source file. What it's done is put everything into one module. As I said, if as you write larger programs, you would want to break that down, but for this, in this case, we will just have everything in one module. It has also written some code for a client as well, so you can interact with your program, and it has written some tests, but we'll come on to those in a little bit later. Okay, you can at the bottom here, you have the terminal for the output. You can connect here to different. You can connect here. I've got a connection to DevNet, for example. So you can use that to connect to different environments. And this is just saying the wallet that I'm using and what the balance is for that. Okay. So let's and we should be able to build this, as you can see by clicking. Oh, okay. No, it doesn't want to build. Okay. All right. Well, before rather than dig into that, what I'll do is I'll talk about what we have within the program, and this will give you a better idea of the way that the program is laid out and the types of things we can have within our program. So at the top we have the imports. So this is with the use keyword here. So what are these for? Well, the very first one here, Bosch, this is the library that is used for serializing and deserializing of instructions and accounts. So we need to have that. Then we have some that are more specific to Solana. So within the Solana program crate, we need details about accounts. So we need to import that. We have this concept, sorry, of the entry point. We'll have a look at that in a second. Specifically, the entry point that is going to return a result for us. We have MSG that is there to output printed output for us. We need program error if we have an error, and then we need public key so we can use an address. Okay, so those are the things we are importing. Then the next thing I have here is the details of the account that I'm going to use for this particular program. So this is the data area within the account. So my program is going to interact with an account. Is going to own that account. It's you can think of it as a data account for this particular program. But within the data area, obviously, I want some structure for that. I want to know what data is actually held there. And so this struct here is defining that for me. So what I have, I've got a struct called greeting account. It's very simple. It's just got a counter in it, which is a U32. So just a numeric value. It's unsigned. We're just doing some process and then counting how many times we're doing that process. So it's quite a simple. It just needs a simple data type for that. Now we need to add this here to say what traits this is going to implement as well, so that we can do the serialization, for example, and we can do debug as well with that. So we need to add that in because we need that for the account. Okay. Now, the next thing we have here, line 19, is a macro entry point, which is saying what the entry point is to this program. So that really allows the system to know where to start with this program. And what we pass into it is the function that is our entry point. So what I'm saying here, we've got process instruction, and that is our entry point. Okay, so that tells the system what the entry point is going to be. So this is where we are going to be starting. So the function itself, process instruction, as you can see, that's our entry point. So we have the 3 arguments that we are expecting. The program ID, which is a public key, it's an address for specifying this program. Then we have a number of accounts. In this case, we've only got one account, but you could be passing in many accounts here. And then similarly, the instruction data that we're passing in. Now, I think in this case, we don't actually use any special instructions because it's just so simple. We're doing everything in one function, but obviously that could have a set of instructions in there. So yeah. Now, you can see from the signature of this function that we're returning program result. And the possibilities for that are either we pass back OK to say that everything worked, and therefore the transaction has succeeded and shouldn't revert, or the other possibility is that we have an error. So we could return a program error instead. Okay, so that's the possible outputs of our function. So what are we going to actually do within this program? It's a very simple program, but we can do a few things. So the first thing that we've got here is something for debugging. It just prints out a message to the console to say that this has started, and then we've got we're actually there in the entry point program. So the entry point to the program. So just a useful thing, just so that you know that your program has started. It's got, at least it's got that far. Okay. Now, what we need to do next then is what we would often do then next will be to look at the instructions. But in this case, we're ignoring the instructions because it's a very, very simple example. But at this point, usually, perhaps you would then be interacting with the instructions. But in this case, we don't really have any instructions to interact with, so we go straight to the accounts. Now, what we do next is to get the account. So we know that there have been there have been one or more accounts passed into this program. So what we do is we want to get the account from that set of accounts. So we can create an iterator here, which goes through this array of accounts to get an account that we are interested in. Okay, so again, this is a fairly common, the fact that there are some accounts coming into your program, but you have to obviously go through those accounts and work out which one you want to deal with. Now, there are some security issues about this, which we'll talk about later. It's obviously important that you know that that you pick out the correct account when you're doing this, and you can't rely on the accounts coming in a particular order generally. So in practice, you would want to be a little bit more careful than we are here, where here we're really just assuming that we've got one account that's coming in, and that's going to be the one that we're interested in is going to be the first one. But normally we would be a little bit more careful than that. Okay. Anyway, so we've created an iterator, and then we get an account from the iterator, by calling this next account info. So this is something that we get from the Solana program crate. We get this details about accounts and of how to handle accounts and to iterate through them. So this will bring us the next account, which in this case is going to be the first one. So this gives us this account here. So this is the variable account, which is a ref to that account info. Okay, so we've now got our account. We can do some things with it. We can read from it. We can write to it, etc. The first thing that we do, though, is look at the metadata effectively within that account. Before we go into the data area for that account, we want to do a check. And the first thing that we want to do is to check that this account is actually owned by this program. Okay, so we check against the program ID that came in, and we check that the owner of this account is this program. So that's a sanity check, something that you should be doing to make sure that you are using the correct account to some extent. I mean, there are other things you would want to check, but certainly a first step in that is that this account is owned by this program. Okay. Now, if it isn't, then we can put a message to the console. So to say that there's something wrong with this account. It's an incorrect account because this program doesn't own it. And then we can return an error, as you can see here. And the specific error that we're returning is given here. So we've imported some errors, from program errors from our crate, and then this one is the one that we're going to use here, saying incorrect program ID. So there's some mismatch here, that this account isn't owned by this particular program. So maybe we've called the wrong program or included the wrong account, but there's something wrong. So we want to say that, and we are returning at this point. So we are returning an error, which is part of or one of the possibilities of program result, and so that will then get picked up by or sent back to the client to say, yes, this failed, and yeah, your client will then know that the transaction will revert, and that it failed, and we've got a specific reason for the failure there. Okay. But hopefully that's not the case. Hopefully we've got the correct account being passed in. We've got the correct program ID. So in that case, we then want to actually get the data area from the account. And so this is what we do with this line here. So it looks a little complex, but it's a standard way to pull the data area from the account. If you remember, the struct we've got for that data area looks like this. So we know that this defines the format of the data within our data area in the account. So that's why we're using that here, the greeting account. So we're putting into that struct the data from the account that we've got, which we then call. We then put in the variable greeting account. And all that our program really does is on the next line, where we just update that, we just increment that. So our program's not doing a great deal, but this, I guess, is the nub of it, the fact that we update the counter. So the greeting account dot counter is this field here. So all that we've done is update that, but that's in our variable here, and then we need to serialize that back to the account itself. So remember, we need to serialize data. Once we've finished with the accounts, they need to be serialized back so that they are being stored efficiently. And you do that in this way. You call the serialize to do that. And once you've done that, that's really the end of it. We can then put out a message to the console just to say how many times we've done this process. So we just print out the counter, and as you remember, well, this works in the same way as well, effectively it's format because we have a placeholder, and so that takes the value from the counter there and prints that out. And then the final thing is that you're going to return an OK to say that everything worked, but we don't have anything to pass back. If you wanted to, obviously you find out how many times you've done this because you get a message in the console, but obviously that only works when you have the console there. So if you wanted to know the details of how it was working, what you would need to do then is to query the account. If you wanted to know the actual value, if your client wanted to know it, then you could do a query from the client to tell you what the latest value of the counter is, and then you could do whatever you like with that. Okay. All right. Okay. Let me just quickly look at. Okay, I think we've got answers for everything. Yeah, I'll try rebuilding. So somebody's saying that it should work 7 time around. No, okay. I don't know. They've got some problem. But anyway, I
Yes,
really
on my side, I refreshed the page and it worked.
Okay.
Maybe you can try.
No. But there wasn't really anything to see in the console. I just wanted to show you what the code was doing generally. So yeah, you've got that. So that's an example of an extremely simple program. As I say, there's lots missing, and as we create more complex programs, you'll see some of the other pieces. But you've got some uh, basics here. You've got the entry point being specified, and you can see what is being passed into the entry point. We've got the fact that that has to return the program result. The fact that that's just going to give us an OK, which does have implications of the way that we write our programs. The fact that we're not returning a value for this. We've got the details, well, the details about the accounts, the fact that we've got potentially a number of accounts and that we have to get the correct account from that. In this case, we're making lots of assumptions, which is potentially quite dangerous. But we have this way to get the accounts by using an iterator, and then we serialize everything at the end, and then hopefully everything is okay. Oh, we also did the check. Yes, we did the check on the program ID, checking the owner of the account as well. So you can see some of the essentials that we've got going, even with a very, very simple example. And you've got the details here of what that account, what the structure of the data within the account should look like. Again, it's very simple because we only have one field, but you could have something much more complex. And you can see some standard ways then of getting the data from the actual account, as you can see here, and then serializing. And also the error handling here. If there's an error, then that will get thrown back up the stack. But you don't have to do your own matching at this point with the accounts to see whether you got an error. You can use the question mark there to handle all of that for you. Okay. So I hope that was useful for you. We'll come back to the playground another time. and look at other things within it. And yeah, I definitely recommend as a starting point, it's pretty good for you to try things out um, and to interact. The alternative, of course, is to use the command line, so you can do that instead. But this is quite a convenient way of doing things. All right. Okay, so where did I get to? Yeah, so that's the end of that. What I think I will do though is I'll quickly start to go through some of lesson 6 notes here, so we can get a bit ahead there, and then we have some practical things for you to do, so we can look at those tomorrow and get some more experience with programs then. But there's just some other things I want to mention around Rust as well. We may also have time to start to look at DeFi on Solana. So if you remember last week, when we started to look at Rust, we found that we have these restrictions applied when we're writing our programs. The compiler is expecting us to follow various rules, and it needs us to do that so that it can make judgments about essentially the lifetimes of the things that we're doing, the variables and the objects that we are using within our code. And there is another nuance about that I want to mention here, because you're going to start to see some of the uh, terminology and notation in the code as you going forward. So I want to just give you an insight into that. So remember, when we have a reference in Rust, we need to be careful and need to make sure that the thing that is referring to is going to be valid for the lifetime of the reference. We don't want to use the reference only to find out that the thing that it was referring to is no longer there on the heap, or has been overwritten. So we have this concept of the lifetime, and usually the compiler can judge this itself and work out what the lifetime is of various objects, because it can see the scope that we have within our functions. So, for example, I think we saw something like this. Yeah, we saw something like this last week, where we had we've got a reference. We've got to use R here to get a reference to X, but at the this line here where we're doing the printing, X has gone out of scope, and so the reference is no longer valid. So this could be um, an error. So usually that would get picked up. So the compiler will know that, and in fact, it uses a thing called the borrow checker to work out the lifetimes of the references, and it will test that for you and tell you that you've got it wrong. So you need to change your code to fix it. So you could fix it like this instead. Showing this on the right hand side here in the comments shows the lifetime of the two lifetimes that are involved. But because the lifetime here B is greater than A, then this is all going to work out okay. But we could have a more complex example that is more difficult for the compiler to reason about. And I've got an example here where we start off, we create two strings, and then we want to see which is the longest string out of those two strings. So we've got a function called longest here, and we can pass references to some strings in there, and we'll pass back a reference to the longest string. Okay, so fairly straightforward. And the way that we can do that is we can simply call the len function here on these strings, and then from that decide which one is the longest string. Okay, so we could do that. We get back the result here, which is the longest one, and then we can print out the whichever it is. Okay. As usual, we are using references here within our function for the arguments because we don't want to take ownership of these strings. We want to still be able to use them outside the function. But the problem with this is that we would get an error because the compiler cannot work out whether this is all valid or not. And it's trying to work out the lifetimes of the references in here, but it can't do it because of the way we've written this function. And that it is really because oh, got some background noise. Could you make sure you're on mute, please? Thank you. This is really because within this function we've got this we've got two branches, so we've got two things that could be returned depending on which one is longest. But it's kind of a we know that we're returning a reference, and we know that we passed in two references, but it's not obvious which which one we're going to return, which and how that relates to the lifetimes of the things we've passed in, etc. So the compiler itself, the borrow checker, has a problem with this. So what we need to do is to help it out and be more explicit about the references that we are using here. And to do this, we can add a special annotation, which is the lifetime annotation. Here's an apostrophe. And that then is followed by some parameter, which can be included within the reference. So you do get, we're getting quite a lot sort of put together here, but you'll see something like this. So it's a reference. It's a reference to an I-32, but what we've got is this special lifetime annotation and this special parameter here, A, to talk about the lifetime of this reference. Also, we can have mutable references as well. But this is something extra that we add to the declaration of our reference so that we can then talk about the lifetime of that reference and use it in comparison to lifetimes of other references. And what that allows us to do then within our function signature is to be more explicit about the references that we have and their lifetime, so that the borrow checker can then make a valid deduction about the code and whether it is correct or not. So all we need to do actually in this case is change the signature of the function here. And what it is doing is saying that because we are using the same parameter here, the A, in this signature, what we're saying is that the lifetime of these references is all the same. This is a little similar actually to the generics that we had when we were parameterizing data types, and we had an example in a struct with some variables, and because we used the same parameter as the data type for those variables, that meant that they would have to be the same data type. And it's a similar thing here, because we're using the same thing here. This is making sure that these all have the same lifetime. So the lifetime of X and Y going in has to be the same, and then the lifetime of the result is going to be the same again. And then the function body is just the same. It's just doing the same thing. But now that the compiler knows this and it can reason about this, then it knows that this is going to be valid, that it can check the lifetimes of the references that are in here, and it can check that we're not going to get a problem because one lifetime is not long enough. It knows enough information about the lifetimes. It knows that the lifetimes of these things are all equal, and therefore it can check and make sure that everything's all right. So yeah, which is what's saying here, that these things are going to have a lifetime as long as this thing here, the A. So yeah, the important point about the way to look at this, the way to think about this, is we're not specifying or not changing the lifetimes themselves. We're not altering the lifetimes of the objects that we're passing into our function. That is all going to be dependent on how they've been declared and used elsewhere. But what we're saying is that we've got some constraints here, and then if these constraints are not met, then that's going to be a problem. But it allows the borrow checker to check these constraints and to make a decision about that. And yeah, as it says here, we don't have to actually know what the lifetimes of these things are, just that these constraints are being met within this function. So yeah, that's that terminology. So you may come across that if you get an error with the borrow checker, then you may need to specify put some constraints around the lifetimes of your references, as you can see there. Okay. All right, let me move on. We've got just a little bit of time left, so I'm going to quickly give you an introduction to DeFi as well today. So I'll just do about 5 minutes of this, I think. So DeFi, one of the major areas now in blockchains, a lot of the use cases are around DeFi, and probably a lot of the projects you will want to write will be in DeFi or involve some aspect of it. There are different parts to it. For example, exchanges, asset management, well, that's smaller now than perhaps it used to be. Stable coins are a large part. Borrowing and lending protocols, and remittance, yeah, all important. But I'd say maybe the top three that people tend to be thinking about are the exchanges, the stable coins, and the borrowing and lending. And it used to be the case that the exchanges that were involved in crypto, we really only had centralized exchanges, which was a little bit odd when you're thinking about these decentralized systems. But if you actually wanted to buy tokens, you had to go to a centralized exchange to do it. Then over time, people worked out ways to create decentralized exchanges as well. And I probably don't need to tell you all of the advantages of these. One point that is certainly true, that this idea of the democratization, it used to be the case if you'd created a token and you wanted if you wanted people to be able to use it, then it would need to be listed on a central exchange, and they charged very high fees for that. So only very large projects with large budgets could actually create and use tokens. But then we got decentralized exchanges coming in. The earliest ones were not great from a user perspective. The way that they worked was that you would want to say you wanted to swap token A for token B. What you would do is you would need to supply token A to the exchange, and then you would be waiting around for someone to come in with token B and then provide the other side of that order and to complete the trade. But what this meant was that, well, it's asynchronous. Effectively, you'd be waiting around for this thing to happen, and particularly if the liquidity of these tokens was low, if there were not many people interested in this trade, you could be waiting a long time. So not, yeah, not very good experience. But that was the initial way that it could happen. So that's really there was a start of decentralized exchanges. And then we got a different type of exchange when Uniswap was invented. Initial ideas fairly early on, 2016, but it was actually launched in 2018, and it absolutely revolutionized the landscape, the DeFi landscape, because it has this thing called an automatic market maker, which means that once you have a pool set up, so a source of tokens that you're going to be swapping, once that has been created, then anybody can at any time go in and swap one of the tokens for one of the other. You can swap token A for token B, and you don't need anyone else to be involved. It will give you a price for that. It's all completely automatic, and it is quite a simple concept as well. And yeah, as it says, it was yeah, truly decentralized. The initial, yeah, Uniswap, you could swap between uh, tokens that followed a particular specification, and yeah, it was robust. One thing I'll just say while I remember it actually is to do with project design and the way that Uniswap was written. The initial design, um, version one, was very limited in what it did. And this is some advice that I've heard about design projects, which I wanted to pass on to you, that when you are creating a project, limit the scope of your initial version uh, very much. So just put out the bare minimum of what your project is going to do, because what you'll find is that once your project is out in the wild and being used, then that will change your opinion about that project and how you want to see it working. And that was the case with Uniswap. Apparently, they very much restricted what it did and kept back a lot of the ideas to see what happened with version one. And then when version two launched, they had that experience of how version one worked, and that helped guide them then into something that was more complete. Well, yeah, automatic market makers, I say, this is something that will allow you to automatically interact with a pool, which is a pair of tokens, and you can exchange one token for another, but a much better user experience. You're not relying on somebody else to provide the market, because there is this automatic market maker doing that for you. Thank you for your attention today. I hope that was useful. Otherwise, I hope you all have a good evening, and I look forward to seeing you tomorrow. Bye bye.